So now that we have some 10-15 minutes left, let me give some history lesson on switch capacitor circuits. So again, we have considered switch cap circuits to realize some particular discrete time transfer functions and so on. But if you look at the history, this all started as usual with radio receivers. In the late 60s, people were trying to make receivers. They wanted to make filters. It was all made using active RC filters using op amps, resistors and capacitors. And when you do that, the center frequency, the bandwidth, everything was inversely proportional to 1 by R times some C, right? It could be square root of R1, R2, C1, C2, but dimensionally it is this, or it is some G by C. Okay. But by now you know that if I have a resistor in one chip, let's say you make something for 1 kilo ohm, it won't be 1 kilo ohm, it's going to be different. And even worse, if I have 100 of such things, each will be completely different. So which means the bandwidth center frequency will be crazily varying across chips. This was a big issue. But what people realized was, on chip, what is extremely well controlled is ratios of two similar quantities, like ratios of two resistors or ratios of two capacitors. That is, if you make this to be 1 kilo ohms, but finally it became 1.2 times 1 kilo ohms. If this was 5 kilo ohm, this will also become 1.2 times 5 kilo ohms. Ratio is constant. This is like, you order some iPhone on Flipkart, the seller cheats you by sending you a brick, you feel sad, but your friend orders the same phone, he also gets the same brick, you're like, yeah, okay, fine. So individually this can go haywire, but if I take the relative things, whatever bad things are happening to that first resistor, same things are happening to this in a proportional fashion, so it's fine. So that kind of made people think, if I can mimic a resistor using a capacitor like this, or a capacitor using a resistor like this, then 1 by RC kind of becomes ratios of R's or ratios of C's. Right? Now think logically, a resistor is something that has no memory. Here I am trying to mimic something which has no memory to create something which has memory. Do you think that is possible? But here I have something that has memory. I am trying to mimic something which has no memory. That is at least logically possible. This is like, if you didn't learn anything for the exam, you don't remember anything, you can't pretend that I know the test and do it. But vice versa works. You can know everything but intentionally fail an exam, right? So this is the logically possible thing, and that's what people did. So to give you a brief glimpse, the idea is this. So let us say you have a voltage source. Let's say it's a DC source V. I have a resistor R. Now if I look at the current versus time, how will it look like? It's a constant voltage. Current will be V by R. Similarly, if I plot the charge versus time, how will the charge look like? Ramp. Charge is integration of current. So we'll do this. Right? Now the goal is try to do something similar using a capacitor. So I have the same voltage source. So I have to mimic this using a capacitor. And typically it is kind of understood using an analogy. So let me use that. One way to visualize or explain a voltage source to a layman is this, right? You can think of it as a reservoir or a tank with infinite volume of water. So here volume of water corresponds to, is a proxy for the charge the voltage source can provide, right? A voltage source can provide infinite amount of charge. So which means the tank has infinite volume of water. Now when I connect a resistor and draw constant current, the analogy is this. Here the water corresponds to charge. Rate of flow of charge is current. So to have a steady current, here I should have a steady flow of water. So let us say I have a small valve here. So I'll have a steady flow of water to ground. So the water flow is constant current. If I look at the volume of water that I am drawing out, that will keep increasing. Fine. Now I want to mimic the same setup using a capacitor. Right. So let's see. I have the same voltage source which is a tank with an infinite volume of water. Now how can I model a capacitor? Remember, a voltage source can store has infinite amount of charge. A capacitor has finite amount of charge. So if this is an infinite well, a capacitor is a small bucket. Right? Now again, what you have to do? You have to mimic this action, which means you have to continuously drain the water from the tank to ground. So here I have the same infinite reservoir. I have a small bucket. How do I drain the water from here to ground? You basically fill this first, dump it, again fill it, dump it. The idea is if I do it quickly, it will appear as though it's kind of continuously done. So if you want to electronically mimic this, what should I do? I should first fill this bucket with the water, which means I should charge this guy. So the same thing now. In one phase, I'll charge this. In the other phase, I'll put it to ground. So I'm filling in water, putting it to ground. Right? So that gives the 2 clock phases. Now, if I try to sketch the charge that is being drawn out of this voltage source as a function of time, how will it look like? In clock phase phi 1, what is the charge drawn? CV in. In clock phase phi 2, what is the charge drawn from here? No, we are not drawing. In clock phase phi 1, phi 2, this is open, right? So in only one clock phase we are drawing it. So if I sketch it, it appears like this. Step, right? So I have CV in. The next clock phase I am drawing 2 times CV in, 3 times CV in. So it will basically look like this. So this is C times V in. This jump is C times V in. Now you can clearly see if I can choose an appropriate C and an appropriate time here, I can kind of mimic this action.
Why are we having jump when we are dumping the charge at the ground already?
No, the point is, let's look at the total charge drawn in one clock period. This is one clock period.
Yeah.
In one clock period, I have just drawn a charge of C times V. That's all. In the second clock period, I am drawing one more charge. That is C times V. The total charge drawn is 2 times CV.
That's what I'm saying. The capacitor shouldn't have any memory, right?
Yeah. We are just looking at, let's say you take a pen and paper, record. First clock period, what is the charge I have drawn? CV in. So I have totally drawn CV in.
Okay.
Second clock phase, one more packet of charge is drawn. So total is 2 times CV. This is the total charge drawn out of the voltage source versus time. This is a rough plot of the voltage source. Yeah. So now if I do this appropriately, I can basically match this curve. Right? And if I do it very fast, from a distance, it will appear as though I am just having a resistor.
It's as though the lamp is being baptized.
What is being?
It's as though the lamp is being baptized.
You can think of it like that, right? Basically, instead of having a constant flow of current, you are doing it in installments. Right? You are dumping it, charging it, pushing the current, charging it, pushing it. So, and now if I actually sketch the current, how will it look like? The charge is basically a step. It will be an impulse train. What will be the area of the impulse train? CV in, right? Remember, area of the impulsive current is essentially the charge. So C times V in is the charge. So at every clock period, I will be kind of drawing this current. It's not matching this thing, but it's okay. You get the point. Okay. And this is what people did. So now, if you look back at a normal continuous time integrator, this was the circuit. Right? Here, if this is R and this is C, what is the transfer function? I mean 1 upon S or C, or something is missing. partially correct. Come on guys, if I have something like this, forget about if I have something like this, V1, what is VO here? It's R1, R2. Minus R2 by R1. So what should be this here? Minus 1 by SR, right? So again here you see that, I mean finally this will be used in a big negative feedback loop to realize a filter. But now we can clearly see here the frequency depends on R and C. It will vary. So again the idea is to replace a resistor with a capacitor. So we just saw how to do that. So the thought process is this same thing. Okay. Now if I do that, you will find that the transfer function of this will be C1 by C2 times so minus 1 by 1 minus blah. So now you see things depend on ratios of capacitors. So this is much better. And this basic idea of kind of mimicking a resistor using an alternating capacitor turns out was first discovered by Maxwell, the same guy who made you learn the 4 equations. But of course he didn't want to make a filter, he was working on something else. He thought, hey, this is a nice thing, look at it. He just told and left. But later on when this was required, people rediscovered and found that it was actually Maxwell had already pointed this out. So bottom line, I mean sometimes you come up with something, it might not be relevant at all in that current thing, but still it is always good to put it out in the public forum and give it to fellow scientists so that later on, maybe 30-40 years later, it will be useful. And one last thing I want to point out, fine point in this. So here, right, yeah, this is the current waveform. Remember, the input is a DC voltage, whereas the output current contains impulse train. So if I look at its frequency spectrum, what all frequency components I'll see? At what all frequencies? Huh? Yeah, 1 by TS is, let us say, Fs. You'll also have at 0, Fs, 2Fs and so on. You applied a DC voltage, the current not only contains the DC component, also the harmonics of Fs. Okay? But if I look at only the DC component of the current, let's call it I0. What do you think is the DC of this current? Basically, you have to find the average of this waveform. What is that? CV in? But CV in is charged, right? I want current. Fine. I mean, again, if you take the area of this, to find the, whatever current, you are going to take the area of this. Average current, you are taking the area of this. And for one period you take it. So if you integrate this, only this part will remain. Integration of impulse is CV in, time period is TS. The other way to see is the charge drawn in one clock period is C times V in, time is TS. Okay. So which means if I look at I0, that is CV in by TS, or I can say C times Fs times V in. Maybe I'll take it to a next page. So I'll write it again. If I look at I0, that is C times V times Fs. That's what I get. Okay. I'll write it C times Fs times V. Both are same. So typically people kind of make loose statements that this means that the equivalent resistance is 1 by Fsc. But strictly speaking, here what I am doing is I am applying an input voltage and measuring a current, right? So denominator is the input, which is the voltage. Numerator is the current that I am measuring, which is the current. What will this give me? Conductance or admittance, whatever. Let's say admittance, conductance, something, right? So this is Fs times C. Okay. Let's say it's conductance G. Right? But this doesn't mean that the equivalent R is 1 by Fsc. There is one minor catch here, because if you have an LTI system, to find the looking in impedance, it doesn't matter if you put in a voltage and measure it, test voltage and measure the test current, or put in a test current and measure the test voltage. Okay. Basically, in the first case, you will be finding I test by V test. That will essentially be conductance. Second case, you will be finding V test by I test. That will be an R. It will be, this relation will be valid. Okay. But when I have a switch capacitor system, is it a linear time invariant system? Let us say this. If I have this, you think it is time invariant? It's time varying, and in fact, this is what we call as a periodically time varying system, because this it kind of repeats itself after one clock period, right? So this is what we call as linear periodically time varying system. And for these LPTV systems, the simplified notion of conductance and resistance, or impedance and admittance, wherein you apply a voltage at DC, find the current at DC, or you apply a current at DC, find the voltage at DC, right? That's what we have done here. Let me call it R0 and G0. So here this will not be equal. And in fact, you can quickly check, right? Here I applied a voltage and measured it. Now you can actually repeat it. Let us say I apply a current here, and you try to measure the equivalent voltage. You will not find that this will be equal. I mean, if you, and then you try to take the ratio. You apply a DC current I0 or I, find the DC voltage V0. This won't be equal to 1 by Fs. And the reason it's happening, because as we saw here, even though I applied a voltage at DC, the current not only contains a DC term, but also contains all other frequencies at Fs to Fs and so on. So only if you define an impedance or admittance which takes into account all these frequencies is when you can claim that the impedance and admittances are inverses of each other. So with LPTV networks, strictly speaking, we can define a matrix of admittance. That is, you can say that if I apply DC at the current, or DC as the voltage, what is the DC current I get? What is the current I get at Fs, 2Fs, minus Fs, minus 2Fs, and so on. Similarly, you apply current voltage at say Fs, and then do all these things. And then you can form a big matrix. Similarly, you can find a similar matrix for Z. Then you will find Z will be inverse of 1. But what we are doing is, we are applying a DC voltage or a DC current, finding the DC part of the final expression. Right here, what we did, we applied a DC voltage and just looked at the DC part of the current. That is as though I am picking out one element from this matrix. Just because these matrices are inverses doesn't mean the corresponding entries are inverted. Okay? So this is a generalized form of impedance admittance. In an LTI network, there is no frequency translation. So you will find that this matrix, if I take a Y matrix, that will be some, I don't know, some Y naught times identity matrix. That is, only if I apply a frequency at Fin, I'll get an output at Fin. There will be no frequency conversions. So only, you'll have diagonal entries here, others will be 0. So here it is fine. Similarly, Z will be some Z naught times I, so it will invert. But the moment you have this kind of time varying systems, the simplistic notion of impedance admittance, wherein you nitpick one element and see it won't be. So bottom line, if you are driving the switch capacitor with a voltage source like this, then I can say that the DC current is FSC times V. That's all. Now we can define V by I naught as 1 by FSC. That is okay. But don't call this as the equivalent looking in resistance. It's a resistance, but it is not the equivalent resistance. That's very tricky term to use. So as long as you drive it with the voltage source, you can make this comment. But the moment this changes to a current source, things go completely haywire. So we'll stop here. We'll continue. should we stop?